السلام عليكم. معكم الدكتور أحمد سيد، أستاذ مساعد الكيمياء التحليلية. هكون معاكم على مدار محاضرتين عشان نشرح الكونسبت بتاع الثيوري والابليكيشن للكومبلكسومتري كجزء من الكورس بتاع PC 203 Analytical Chemistry. Today we shall discuss the complex formation titration part of Analytical Chemistry course. Two lectures will be taken in this concept. First, the theory and the application will be studied. We have studied before theories of acid-base titrations from those Lewis theory. Complexometry titration is considered to be one of Lewis theories, where the acid part is the electron acceptor, the basic part is the electron donor. We shall review together, just for our memory, the types of bonds. There is an ionic bond, such as the sodium chloride. There is a covalent bond between two atoms to form a molecule, such as the oxygen. And in our case, in complexometric titration, the type of bonds between the two moieties forming a complex is a coordinate bond between what is called the central metal ion and a ligand. Definition. Complexometry is a volumetric method, involves reaction of metal with ligand to form a complex, where the central metal ion is the electron acceptor, the ligand is the electron donor. The ligand should contain a donating atom, which donates the electron. They are called a heteroatom, such as the nitrogen, oxygen, and sulfur, to form the coordinate bond between the ligand and metal. So, complex formation is a type of acid-base reaction according to Lewis theory, where metal ion is Lewis acid, the electron acceptor, and the ligand is Lewis base, which is the electron donor. At the end, they form together a weakly ionizable stable complex. Of course, for a reaction to be completed, the end product should be more stable than those moieties at the beginning of the reaction. Simple diagrammatic form where the central metal ion, which is usually positively charged, either 2, 3, 4 positively charged, with a ligand which donates the lone pair of electrons to form a coordinate bond, thus forming a complex which is weakly dissociated stable compound. Types of ligands. Ligands could be categorized or classified depending on the charge. For example, neutral ligand as the ammonia, charged ligand as the cyanide. In order to make this a little bit easier how they are bonded together, you can see the copper, which is 2 positively charged, is surrounded or coordinated, bonded by 4 moieties of ammonia. A question. Well, what's the valency of the formed complex? Usually, the valency of the complex is the algebraic sum of the valency of its components. In our case here, the copper amine complex will take, as a complex, will take 2 positively charged because the ammonia are neutral and the copper is 2 positively charged. Coordination number. Coordination number is the number of binding sites between the central metal ion and the ligand. It could be 2, 4, 6. As a definition, coordination number is the number of bonds formed by the central metal ion with ligand. Formerly discussed example, the copper amine, you can see that the coordination number here is 4. Why 4? Usually we say that it is double the valency of the central metal ion. Copper here is 2 positively charged, so the coordination number of copper is 4. It depends on steric factors and electronic configuration of the metal. Typical values of coordination number are 2, 4, or 6 even numbers. Another example, like the silver and the cyanide, you will see that it should take, the silver should take 2 ligands or 2 cyanide moieties. The end result of the valency of this complex is -1. Why? We took 2 parts of the cyanide multiplied by -1 and 1 part of the silver, which is 1 positively charged, so the end result will be 1 negatively charged complex of silver cyanide. Same goes here for copper and cyanide, and same here with silver and amine. Aqua complex. Usually our metal sample is dissolved in water. Since water has the oxygen, and oxygen is one of the heteroatoms previously discussed, they will form a complex with the metal called aqua complex. This complex, either it is labile or it is non-labile. Labile, that means that the water molecules surrounding the metal forming the aqua complex are easily substituted by any other ligand that could enter the reaction. It doesn't need any vigorous or extensive conditions of the reaction. However, non-labile or inert aqua complexes, they are very slow to be replaced. Here the ligand has some difficulty to replace the water molecules, and it needs heating, sometimes vigorous shaking, just to be replaced. In that case, we call it a non-labile or inert aqua complex. These metals usually form non-labile or inert aqua complexes. Aluminium, cobalt, chromium, and ferric should be good memorized, because we will see in the second lecture how we could analyze it. It will not be analyzed directly by simple titration. So aqua complexes is the tendency to form complex is inherent property of all metal. Therefore, metals formed with water, aqua complex, which is solvated metal ion, as oxygen of water donate electrons to metal ions. Complexation reaction is a replacement of solvent molecules by a ligand. This replacement by a ligand can be repeated several times, but not forever, till the central metal ion takes an optimum number of ligands governed by the maximum coordination number of the metal ion. Just to remind you, usually the coordination number is double the valency of the central metal ion. So the aqua complexes could be divided into labile or inert non-labile. Some aqua complexes undergo substitution reaction very rapidly, and the complex is said to be labile, for example, copper and nickel. Others undergo substitution reaction very slow, and the complex is said to be non-labile, such as aluminium, chromium, ferric, and cobalt. Another classification of the ligand is the point of attachment between the ligand and the central metal ion. So if the ligand is attached to one point with the central metal ion, it is called unidentate. If it is attached with more than one point, then it's called polydentate. Then the polydentate is subclassified into bidentate, tridentate, tetradentate, depending on the number of points of attachments with the central metal ion. Unidentate ligand, diagrammatic form just to make it a little bit easy. For central metal ion, one point of attachment forming the metal ligand complex. On the other hand, polydentate ligand form a chelate. A chelate is a ring structure weakly dissociated complex where the ligand is a polydentate attaching the metal with more than one point, and in such case the ligand is called a chelating agent. Examples from the polydentate ligand. Let us begin with the bidentate ligand, such as ethylene diamine with copper. It forms a ring structure, a chelate. 8-hydroxyquinoline, ring structure with magnesium. Orthophenanthroline with ferrous, also a ring structure chelate with the ferrous. 6-membered ring, such as acetyl acetonato. Tridentate ligand, for example, diethylene triamine. Tetradentate ligand, like triethylene tetramine or triene. I do not need that you memorize these structures, only you should know the classification and an example from a compound that is related to each subclassification. Another topic is the stability of the complex. Which do you feel or you see it will be more stable? A central metal ion attached to 2 ligands, or 4 ligands, or 6 ligands? Well, eventually, as the points of attachments increase, the stability of the complex also increases. So, by default, you will see that the polydentate ligand, either bi, tri, or tetradentate, are more stable if they form a complex with a central metal ion rather than the unique ligand. Chelates are more stable than complexes formed by unidentate ligand. Again, a chelate is a complex that is formed of a central metal ion and a polydentate ligand. Why? Due to presence of more than one point of attachment of the ligand and the central metal ion. Therefore, a polydentate ligand is preferable as a titrant if compared with unidentate ligands because they react with the metal completely in one step and drop it, forming stable complex leading to sharp endpoints. On the other hand, any stepwise formation of the complex with a unidentate ligand gives no sharp endpoint. And what we should know that for quantitative determination to know the concentration of our sample, we should apply a polydentate ligand to give a sharp endpoint so that we can take the reading more accurately. Simple comparison between the types of complexing agents or the ligands, you will see that the unidentate ligand attached to central metal ion form one point of attachment, forming a soluble complex using ammonia, water, ceramide, or halides as ligands, which are inorganic molecules. And an example of that is the formation of copper amine complex. On the other hand, polydentate ligands, they are attached to the central metal ion from more than one point of attachment, forming a ring structure complex with metal, which is called a chelate. Ligands at this stage are called chelating agents, and complexes are called chelates. Chelating agents are inorganic molecules which are usually water insoluble, could be determined with gravimetry, but that will be later studied. Except a very important polydentate ligand is water-soluble, universal titrating agent called EDTA. In titrometry, we always use EDTA for determination of the metal. In such case, the water-soluble polydentate ligand is called sequestering agent. This is a simplified table which gives you a quick comparison at different points between the unidentate and the polydentate, taking up from the point of attachment, the reaction, how it will be, the inflection of the titration curve, endpoint stability of the formed complex, titrometric reaction, and of course some examples. Well, how do you think about these questions? Compare between unidentate and polydentate ligand. You will discuss the previously illustrated points in the table. Ammonia couldn't be used as a titrant. Well, ammonia is a unidentate ligand, and unidentate ligand results in a flow reaction, stepwise, giving no sharp endpoint. Another question, polydentate ligands are used as titrant. We give the advantages of the polydentate ligand, more than one point of attachment, sudden inflection of the curve, one step reaction gives sharp endpoint. Polydentate ligands form more stable complexes than unidentate ligands. All of these questions could be answered with what we have just discussed between the comparison of the polydentate and the unidentate ligands. Well, what are the factors affecting stability of the complex? Stability of the complex is, since the complex is formed between the metal and the ligand, then there are some factors affecting the metal and some factors affecting the ligand. The acidity of the metal, the basicity of the ligand. For the metal, the ionic size and the ionic charge differ compared to the stability of the complex. For the ligand, the size of the ligand, structure of the final chelate, and extent of chelation also differ in the stability of the complex. Factors affecting the stability of the complex. When we should discuss the central metal ion, we say that the higher the acidity or electronegativity of the central metal ion, the higher the stability of the complex, which means that if we increase the density of the positive charge on the central metal ion, it will increase the stability of the complex, because in that case, the central metal ion will grab or take the electrons more rapidly and more aggressively. It is governed by a simple formula or equation where we say the intensity, which is F, is directly proportional to the charge present on the central metal ion, inversely proportional to the radius of the central metal ion. That means if a central metal ion are dense in charges, it will form eventually a more stable complex. If the central metal ion is low in the size or with smaller size, it will also form eventually a stable complex. So the central metal ion of small radius and high positive charge has high ability to form stable complex. Also, just for your information, the principal quantum number, it's a unique number that is present for each central metal ion. They differ also in stability, just to know this phrase as it is. Question. The acidity, what do you think about the acidity of these two central metal ions having the same charge, but they differ in the size? Of course, the smaller the radius, the high density of the positive charge, eventually forming a more stable complex. On the other hand, two with the same radius, the central metal ion, but one of them is more positively charged, this one will form the more stable complex. For example, the ferric cyanide complex is more stable than the ferrous cyanide complex. Again, the formula which discuss the same theory. The second factor affecting the ligand, well, it's the basicity of the ligand. Basicity of the ligand is its electron donating ability. Therefore, ligands must contain electron donating atoms, which are called heteroatom, nitrogen, oxygen, sulfur, and halides. Organic ligands must contain coordinate or acidic group, or both of them. They are classified as such in the table. The ligand, if it is large, but not very large, it will easily lose the electrons than a smaller ligand, and thus the electron donating ability will increase and the basicity of the ligand will also increase, giving a more stable complex. The size of the ligand. The large, very large, bulky ligands form more stable complexes than smaller ones due to the steric effect. Here we can see the ethylenediamine easily donating the electrons, forming stable complexes, while here the steric effect doesn't give much space or freedom for a complex to be formed. Structure of the final chelate. The stablest chelates are formed by ligands that form saturated 5-membered ring, or by ligands forming unsaturated 6-membered ring, like the copper, ethylenediamine, and acetylene acetylated. Surrounding conditions. Some stable complexes may not be stable under other conditions. For example, the cobalt amine is unstable in acidic solution, but stable in water with neutral pH. Editor. Editor as a titrant in complexometric titration is a universal titrant which is usually used in all titrometric complexometric reaction. Editor is abbreviated. This is the abbreviation of ethylene diamine tetraacetic acid. The disodium salt of editor is soluble in water, what we have called a chelating agent that is soluble in water, sequestering agent. It forms soluble chelates and is the most suitable titrant. Do not need you to memorize the structure of editor. However, to simplify things, this bulky part of the structure we abbreviated by Y. So the disodium salt of editor is abbreviated by sodium, hydrogen, and Y. A commercial name of the editor is called Complexome 3. Please memorize that, Complexome 3. The following equilibrium is established when sodium, hydrogen, and Y, which is the editor, is dissolved in water. Why using the editor? It has low price. It forms a special hexadentate structure with the central metal ion. It is bonded by 6 points of attachments, either horizontally or vertically, to form a spider web on the central metal ion. It is a typical sequestering agent. It was found that editor reacts with different central metal ions in the ratio of 1:1, irrespective to the valency of the central metal ion. You can see here, all central metal ions with different valencies are treated equally with the editor, liberating 2 parts of the hydrogen. Therefore, and this is important characteristics should be memorized for editor. Editor is not selective reagent. Central metal ion displays 2 parts of the hydrogen, producing 2 mole of hydrogen. The reaction between editor and the central metal ion is according to the molecular weight. Reacts in ratio of 1:1 with all metals, therefore editor is used as molar standard. Formation or dissociation of the formed complex is affected by pH. So, the reversibility of the reaction can be prevented by addition of buffer or alkali to shift the reaction forward, hence stability of chelate is increased. Always consuming the hydrogen and always shifting the reaction forward towards the formation of a complex. The ligand, if it is large but not very large, it will easily lose the electrons than a smaller ligand, and thus the electron donating ability will increase and the basicity of the ligand will also increase, giving a more stable complex. Stability and stability constant of complex. Stability of a complex is evaluated by its stability constant or formation constant. Assume a reaction between central metal ion and editor. According to the law of mass action, the K equilibrium is the value of dividing the parts after the reaction over the parts going into the reaction. So the K equilibrium represents the rate of formation of the complex. It is called as formation constant or stability constant. The greater the K stability, the greater the rate of forward reaction and stability of the formed complex. In alkaline buffered medium, the K stability is represented as follows. We consume the hydrogen, and the reaction is now between the division of the molar concentration of the complex, of the formed complex, divided by the molar concentration of each of the central metal ion and the editor. It was found that reaction producing complex with K stability equals or more than 10 to the power 8 is sufficiently complete at the equivalence point, which is the end point, for a feasible titration. K instability is the opposite of K stability, 1 over K stability, just for your information. Here in this table, we can see a formation constants of various metal chelates with editor. Just take a look at it. It's not for memorizing. However, you can see very clearly that the values of the K stability or the formation constant are high when the valency of the metal, the central metal ion, is high. Editor. Editor as a titrant in complexometric titration is a universal titrant which is usually used in all titrometric complexometric reaction. Editor is abbreviated. This is the abbreviation of ethylene diene tetraacetic acid. The disodium salt of editor is soluble in water, what we have called a chelating agent that is soluble in water, sequestering agent. It forms the effect of pH on the complexometric titration. Again, a titration curve here is illustrated. The effect of pH on the stability of complex, which represent titration of calcium salts at different pH values. It is clear from the titration curve that the stability of the metal editor is increased by increasing the pH. Well, if you're a little bit tired, take a 5-minute break and return back to complete the lecture. How to detect the endpoint? Well, in complexometric titration, we usually use indicators, metachromic indicators, such as meroxide, EBT, xylitol orange, specific indicators, such as thiocyanate salicylic acid, acid-base titration, electrochemical reaction. Well, let us discuss them. Question. The acidity, what do you think about the acidity of these two central metal ions having the same charge, but they differ in the size? Of course, the smaller the radius, the high density of the positive charge, eventually forming a more stable complex. On the other hand, two with the same radius, the central metal ion, but one of them is more positively charged, this one will form the more stable complex. For example, the ferric cyanide complex is more stable than the ferrous cyanide complex. Again, the formula which discuss the same theory. So, for the detection of the endpoint, the metal indicators are complexometric titration. The endpoint is detected by using metal indicator. Metal indicators are usually complexing agents, ligands. The function of metal indicator can be summarized by the following equation. Metal, central metal ion, with the indicator forming a metal indicator complex, which has a specific color. Then the editor replaces the indicator and forming a metal editor complex and leaving the indicator free, which should have another color. Therefore, for successful use of metal indicators, the following requirements must be fulfilled. Number one, reaction between indicator and the central metal ion must be specific, or at least selective. Central metal ion editor complex must be more stable than metal indicator complex. Metal indicator complex must be of sufficient stability. That means it shouldn't be dissociated to give free indicator before complete reaction between the metal indicator and the editor. Number four, the color of the metallized indicator and free indicator must be sufficiently different and intense enough, sharp and point. So I highlighted the most important wording in each point: specific, stable, sufficient stability, and sharp endpoint, the 4S rule. Types of metal indicators. Metallochromic indicators. These are called chromodies or mordants. This type of indicators exhibit a color in free form which is different form from that of metal indicator complex. The chemical structure of these indicators contains acidic and or coordinate basic group, which usually hold heteroatoms. These groups are joined in the electronic configuration system of the indicator. Therefore, any change on this electronic configuration could take place within the pH change. Well, if you can remember, the reaction between the metal and central metal ion and the editor releases hydrogen, and hydrogen could change the pH of the medium. Therefore, it is very important to use a buffer or alkali in the complexometric titration. Why? So it can consume the liberated hydrogen from the reaction of the central metal ion and editor. Thus, the reaction and the change of color of the metallochromic indicator is only due to the end point, not due to the pH change. General principle. For determination of central metal ion, we add the indicator, forming a metal indicator complex, which in this case, for example, is purple in color. Then we titrate it with a complexing agent, like the editor, which is also called the sequestering agent, if you can remember. It consumes the metal indicator and giving a free indicator which should have a different color than the metal indicator complex. In that case, for example, it's now blue. So the requirements of the metal indicator before its rule, again, it should be specific for the metal, should be sufficiently stable, not to be detached unless the reaction is complete with the editor. The stability of the editor metal complex should be more than the stability of the metal indicator complex, and a different color should be present in case of the metallized form of the indicator and the free form. It was found that editor reacts with different central metal ions in the ratio of 1:1, irrespective to the valency of the central metal ion. You can see here, all central metal ions with different valencies are treated equally with the editor, liberating 2 parts of the hydrogen. Therefore, and this is important characteristics should be memorized for editor. Editor is not selective reagent. Central metal ion displays 2 parts of the hydrogen, producing 2 mole of hydrogen. The reaction between editor and the central metal ion is according to the molecular weight. Reacts in ratio of 1:1 with all metals, therefore editor is used as molar standard. Formation or So the following equations represent titration of central metal ion against editor in presence of peroxide indicator. Again, the central metal ion is reacted with the indicator, forming a metal indicator complex. Then editor is being added until the reaction is finished. Metal and editor complex is now formed, and the free indicator is liberated with different color. To see and memorize, please, the difference in colors. Peroxide, copper, cobalt, and nickel complexes are yellow. Peroxide free is purple. Peroxide calcium complex is pink. Peroxide free is purple. We usually use fresh saturated aqueous solution or use fine powder of the peroxide. Here we can see the difference in the colors between the metallized form of peroxide and the free form of peroxide in case of calcium. Second metallochromic indicator we have is eriochrome black tea, or EBT as abbreviated, or it's also called solochrome black. It is used for determination of magnesium, zinc, cadmium, lead at pH 10. Please memorize the central metal ions for EBT and the pH range or the pH that it works in. It also contains 2 replaceable hydrogens. The equation here, we select in the middle form of the indicator at pH 7 to 11, above which orange form, below which red wine. The following equations represent the titration of central metal ion with editor in presence of EBT at pH 7 to 11 using ammonia buffer at pH 10. Well, EBT cannot be used for determination of copper, cobalt, nickel, ferric, and aluminium. Why is that? Because these central metal ions form irreversible complex with this indicator. That means even if we put editor will not substitute the indicator from the central metal ion indicator complex. That means they block the indicator. Therefore, the central metal ion should be masked using cyanide before titration involving the use of EBT. This will be thoroughly discussed next lecture. EBT also should be used as fresh aqueous solution or fine powder. Here is the difference in color between the metallized form and the free form of the indicator. Third metallochromic indicator we have is xylenol orange. Xylenol orange is used for determination of bismuth and lead, where the difference in color, also please memorize that, the difference in color between the metallized form and the free form is usually from red to yellow. This table resembling the metals that could be analyzed using xylenol orange, the conditions that it is put in, which usually is the pH range, using, for example, pH 1 to 3 nitric acid, or pH 5 to 6 using hexamine solution, or 5 to 4 using acetate buffer. The change of color is usually from red to yellow, and some exceptions from purple to yellow, such as the ferric and the mercury. Questions? Why we should carry out complexometric titration in buffered medium? We should state two answers. The first answer is to consume the hydrogen liberated from the reaction between the central metal ion and the editor. Why? So that it could shift the reaction forward towards the formation of stable complex. The other answer is forward reaction with optimum stability, yes, sharp change on and color change due to complexation reaction, since the metallochromic indicators are affected by pH. EBT cannot be used for determination of copper, cobalt, nickel, ferric, and aluminium. Why is that? Because they block the indicator. They form an irreversible stable complex with the indicator, and no endpoint will result. So the left part is now discussed. Now the right part is discussed in brief as specific indicators such as thiocyanate and salicylic acid. They are specific for ferric, acid-base, and electrochemical reaction. Specific indicators, thiocyanate. Of course, you have heard about the blood red color that is formed between the ferric and the thiocyanate. Here, the endpoint will not be change of color, but it will be a decolorization of this blood red complex color. The same goes with the salicylic acid, also with ferric, but it gives a violet color, and the endpoint is detected by decolorization of this violet color. There are two other methods to detect the endpoint, which is the acid-base titration, acid-base in complexometry. Yes, if you remember, the reaction between the central metal ion and the editor produces 2 gram mole of hydrogen. This hydrogen liberated is equivalent to the molar concentration of the metal. So we can titrate the hydrogen liberated against standard alkali in presence of an acid-base indicator such as methyl pred. And this will be equivalent to the concentration of the metal. Another way to detect the endpoint that we can use electrochemical reaction, potentiometric and conductometric techniques, which you will study it thoroughly in the instrumental part, I think next year or something like that. Well, we have finished today's lecture. I hope that you have learned a little bit from it. I hope that I was clear enough. For any kind of questions, please do not hesitate to ask. Thank you.